Divisibility proofs. 30 is divisible by 6 because when 30 is divided by 6, the remainder is 0. Another way of saying this is that 30 is divisible by 6 because we can write 30 equals 6 multiplied by a for some a value element of the integer set. We know that a is equal to 5 because 6 times 5 is 30. But this is not important. Saying that 6 is a factor of 30 is equivalent or equal to saying that 30 is divisible by 6. In the same way, if f of k is divisible by 8, then we can write f of k equals 8 multiplied by a for some a value, an element of the integer set. Likewise, if f of k is divisible by 11, then f of k is equal to 11 multiplied by a for some a value, element of the integer set. So some positive or negative whole number. We will use this definition of divisibility in the proof by induction questions to follow. A typical such question would be, prove by induction that 3 to the power of 2n minus 1 is divisible by 8 for all n values, elements of the natural number set. So for all positive whole numbers. We should note the following. If n is in the index, try to write each index as n exactly. So here, 3 to the power of 2n is equal to 3 to the power of 2 raised to the power of n, which is equal to 9 to the power of n. Thus, Pn is 9 to the power of n minus 1 is divisible by 8 is a better way of writing the proposition. Write the assumption with an equal sign and rearrange to get a single term on the left-hand side, the LHS. Here we have P of k is 9 to the power of k minus 1 is divisible by 8, i.e. that is 9 to the power of k minus 1 equals 8a for some a value element of the integer set, i.e. that is 9 to the power of k equals 8a plus 1. So we just brought the minus 1 over the equal sign, it became plus 1. So we have the 9 to the power of k on its own. We want a single term on the left-hand side. In the p of k plus 1 expression, break down the terms so that the 9 to the power of k is visible. Then substitute 8a plus 1 for this term and show that 8 can be taken out as a factor. So since you will have stated something along the lines of 9 to the power of k equals 8a plus 1, you can swap the 9 to the power of k for 8a plus 1. Prove by induction that 3 to the power of 2n minus 1 is divisible by 8 for all n values, elements of the natural number set. So P of n is 3 to the power of 2n minus 1 is divisible by 8. S, the starting number is equal to 1, as the natural numbers are 1, 2, 3, ... Or P of n is 9 to the power of n minus 1 is divisible by 8. So we've swapped this for this because 3 to the power of 2n can be rewritten as 3 squared raised to the power of n, which is 9 to the power of n. So this is a better way to write it. So P of n is 9 to the power of n minus 1 is divisible by 8. So step 1, we substitute S1. So we sub in 1. So P of 1 is equal to 9 to the power of 1. So swapping that n for 1 minus 9, which is 9 minus 1, which is 8. And 8 is divisible by 8. So this is true. So P of n is 9 to the power of n minus 1 is divisible by 8. So step 2, assume P of k is true, i.e. that is that 9 to the power of k minus 1 is divisible by 8. So basically just swap the n there for k. So 9 to the power of k minus 1 is divisible by 8 i.e. that is 9 to the power k minus 1 equals 8a. So we're just swapping is divisible by 8 for equals 8a. So this is for some a value element of the integer set. And next we just get the 9 to the power k on its own. So we bring the minus 1 over the equal sign and we get plus 1. So 9 to the power k equals 8a plus 1. So this is our assumption, and this is what we want to prove. So we want to prove p of k plus 1. So we basically just swap that k for k plus 1. So we want to prove that 9 to the power k plus 1 minus 1 is divisible by 8. This is what we want to prove. And we're going to use the assumption to help us do that. So this is our assumption, and this is what we want to prove. So we have 9 to the power of k plus 1 minus 1. So this is what we're trying to prove. So we have 9 to the power of k plus 1 minus 1. So we're going to rewrite 9 to the power of k plus 1 as 9 times 9 to the power of k. So 9 on its own is really 9 to the power of 1. So checking, we multiply these out. 9 to the power of 1 times 9 to the power of k. Multiplying powers with the same base, we add the powers, we add the 1 and the k. So get 9 to the power of k plus 1. And then we still have minus 1. Now in our assumption, we stated that 9 to the power of k, we got this on its own, is equal to 8a plus 1. So we're going to swap that 9 to the power of k for 8a plus 1. So we still have the 9 in front and the minus 1 at the end. So 9 times 8a is 72a. And 9 times 1 is 9, minus 1 is 8. So now we're going to factorize. We're going to take 8 outside the bracket, that's our HCF. So 8 into 72a leaves us with 9a, and 8 into 8 goes once. So we have 8 times 9a plus 1, and we're going to swap the 9a plus 1 for b. So b is some b, which is an element of the integer set. It doesn't matter what it is, but it's some value. So you end up with 8 times b. Thus, 9 to the power of k plus 1 minus 1 is divisible by 8, because we ended up with 8 times something. It doesn't matter what this is, but anything multiplied by 8 is divisible by 8. So we got this, 9 to the power of k plus 1 minus 1, to equal 8 times something. So if whatever this something is, in this case we're just going to call it b, can be multiplied by 8, then this must have a factor of 8. This is divisible by 8. So thus 9 to the power of k plus 1 minus 1 is divisible by 8, hence p of k plus 1 is true, assuming p of k is true. Conclusion, thus p of n is true for all n values elements of the natural number set. Prove by induction that 3 is a factor of 7 to the power of n plus 2 to the power of 2n plus 1 for all n values elements of the natural number set. So is a factor of really means is divisible by. 3 is a factor of is another way of saying is divisible by 3. So p of n, so what we're given is 7 to the power of n plus 2 to the power of 2n plus 1 is divisible by 3. And s is equal to 1. The starting number is 1 because 1 is the first number in the natural numbers. So this can be rewritten as 7 to the power of n plus 4 to the power of n plus 1. So 2 to the power of 2n can be rewritten as 2 squared raised to the power of n, and 2 squared is 4. As 2 to the power of 2n is equal to 2 to the power of 2 raised to the power of n, and 2 squared is 4, so it's 4 to the power of n. So that's how this becomes this. So we have Pn equals 7 to the power of n plus 4 to the power of n plus 1 is divisible by 3. So step 1, we substitute in s equal to 1, which is the starting number. So p of 1 is 7 to the power of 1, so swapping that n for 1, plus 4 to the power of 1, swapping that n for 1, plus 1 equals 7 plus 4 plus 1, which is 12. And 12 is divisible by 3, so it's true. Step 2. Assume p of k is true, i.e. that is 7 to the power of k plus 4 to the power of k plus 1 is divisible by 3. So we basically just swapped each of these n's for k. So is divisible by 3 we can rewrite as equal to 3a for some a value element of the integer set. And then all we want to do is get the 7 to the power of k on its own. So we bring down the 7 to the power of k equals 3a. Well, the 3a was already on the right, so we don't need to change signs. We bring the 4 to the power of k over the equal sign, it becomes minus 4 to the power of k. And we bring the plus 1 over the equal sign, it becomes minus 1. So we have 7 to the power of k equals 3a minus 4 to the power of k minus 1. So we want to prove that p of k plus 1 is 7 to the power of k plus 1 plus 4 to the power of k plus 1 plus 1 is divisible by 3. So what we've done is we've just swapped each of these k's for k plus 1. So this is what we assume, this is our assumption, and we're going to use it to prove this. So again, this is our assumption, and we're going to use it to prove this. So we're going to take the left-hand side, so we have 7 to the power of k plus 1, plus 4 to the power of k plus 1, plus 1. So we're going to rewrite this as 7 to the power 1 times 7 to the power k, because 1 plus k is k plus 1. So 7 to the power k plus 1 is 7 times 7 to the power k. And we add on 4 times 4 to the power k. So 4 to the power k plus 1 can be rewritten as 4 to the power 1 times 4 to the power k, because 1 plus k is k plus 1. And then we just have the plus 1. Now up here we got the 7 to the power k on its own. So we can swap 7 to the power k for 3a minus 4 to the power k minus 1. So we have 3a minus 4 to the power k minus 1 in brackets. Then we bring down the plus 4 times 4 to the power k, and we bring down the plus 1. Next we multiply out the brackets. 7 times 3a is 21a. 7 times minus 4 to the power k is minus 7 times 4 to the power k. And 7 times minus 1 is minus 7. And then 4 times 4 to the power k, we just leave as 4 times 4 to the power k. And we bring down the plus 1. And we bring down the 21a. Minus 7 times 4 to the power k plus 4 times 4 to the power k is minus 3 times 4 to the power k, because 7 plus 4 is minus 3. And then minus 7 plus 1 is minus 6. So we have 21a minus 3 times 4 to the power k minus 6. Next we're going to factorize. We're going to take out the highest common factor, which is 3. 3 into 21a leaves us with 7a. 3 into minus 3 times 4 to the power k is minus 4 to the power k. And 3 into minus 6 is minus 2. Next we're going to substitute 7a minus 4 to the power k minus 2 for b. So b is sum b, which is an element of the integer set. It doesn't matter what it is. So we end up with 3 times b. So we have 7 to the power k plus 1 plus 4 to the power k plus 1 plus 1 equals 3b. So 3 times something. It doesn't matter what that something is, but we know it's equal to 3 times something, which means that 3 will divide into this. Thus, 7 to the power k plus 1 plus 4 to the power k plus 1 plus 1 is divisible by 3. Hence, p of k plus 1 is true, assuming that p of k is true. Conclusion. Thus, p of n is true for all n values elements of the natural number set. Prove by induction that 2n to the power 3 minus 3n squared plus 1 is divisible by 6 for all n values elements of the natural number set where n is greater or equal to 2. So p of n is 2n cubed minus 3n squared plus n is divisible by 6, where s is equal to 2. So n has to be greater or equal to 2, so the starting number is 2. So step 1, we swap each of these n's for 2. So p of 2 is 2 times 2 cubed minus 3 times 2 squared plus 2, which gives us 16 minus 12 plus 2, which is 6, which is divisible by 6, so it's true. 6 is divisible by 6. Step 2, assume p of k is true, i.e. that is that 2k cubed minus 3k squared plus k is divisible by 6. So we're basically just swapping each of these n's for k. So is divisible by 6 can be rewritten as equals 6a for some a value element of the integer set. So next what we want to do is get the 2k cubed on its own, since that's the highest power. So we have 2k cubed equals 6a. The 6a was still on the right, so we don't change the sign. Minus 3k squared comes over the equal sign, becomes plus 3k squared. Plus k comes over the equal sign, becomes minus k. So we have 2k cubed equals 6a plus 3k squared minus k. So this is our assumption, and we want to prove p of k plus 1. So we basically swap each of these k's for k plus 1. So we want to prove that 2 times k plus 1 cubed minus 3 times k plus 1 squared plus k plus 1 is divisible by 6. So this was our assumption, and this is what we want to prove. So we take the left hand side, so we have 2 times k plus 1 cubed minus 3 times k plus 1 squared plus k plus 1. So the first thing we're going to do is expand the brackets. So k plus 1 cubed gives us k cubed plus 3k squared plus 3k plus 1, and we still have the 2 stuck on in front. K plus 1 squared is k squared plus 2k plus 1, and we still have the minus 3 stuck on in front. And then that's going to be added to k plus 1, so we just have k plus 1. Next, we simplify. So starting with the k cubed, so we have 2 times k cubed, so we bring that down here, 2k cubed. Then the k squared, so we have 2 times 3k squared, which is 6k squared. And then minus 3 times k squared is minus 3k squared. And 6k squared minus 3k squared is 3k squared, so that's where that comes from there. Then the k's. 2 times 3k is 6k, and minus 3 times 2k is minus 6k, so they'll cancel. So we just have the k. And then the constants, so 2 times 1 is 2, minus 3 times 1 is minus 3, and plus 1 gives us 0, so we end up with no constants. So we have 2k cubed plus 3k squared plus k. So I would suggest doing this out separately, maybe as rough work, or doing a few extra steps, because it is easy to go wrong with these questions because there's a lot of working out to do. Now up here in our assumption we got 2k cubed on its own, and we said that 2k cubed was equal to 6a plus 3k squared minus k. So we're going to swap the 2k cubed for 6a plus 3k squared minus k. We bring down the 3k squared, we bring down the plus k. Next we're going to simplify, so we bring down the 6a, 3k squared plus 3k squared is 6k squared, and minus k and plus k will cancel. So we have 6a plus 6k squared. So next we're going to factorize, so we take out the 6, which is the HCF, the highest common factor. 6 into 6a leaves us with a, 6 into 6k squared leaves us with k squared. Now we're going to substitute a plus k squared for b. So b is sum b, which is an element of the integer set. It doesn't matter what it is. What we care about is that we have 6 multiplied by something. So we have this equal to 6 multiplied by something, which means this is divisible by 6, which is what we wanted to prove. Thus, p of k plus 1 is true, assuming p of k is true. Conclusion. Hence, p of n is true for all n values elements of the natural number set where n is greater or equal to 2.